Hello everyone, my name is Jiangong Chen, a PhD student at the Pennsylvania State University. Today I'm going to present our work, LLMER, Crafting Interactive Extended Relative Worlds with JSON data generated by large language models. It's a collaborative work with my lab mate Xiaoyi, my advisor Dr. Bin Li, and Professor Tian from George Washington University. With the recent advancements on generative AI, people now use generative AI to create various contents during their daily lives. For example, they can create plain text for conversation, coding scripts, images, or audios. On the other hand, extended reality provides immersive experience for users to interact with virtual objects on top of real-world environments. For example, they can use their hand to grab a virtual cube, create a hammer rotating around their fingers, and create a virtual table tennis table on top of real-world floors. The goal of our paper here is to integrate generative AI with extended reality environments, and thus the users can freely create or edit objects or animations in the XR environments. Before diving into the details of our paper, let's do a quick recap of related work. Many researchers now develop LLM agents to autonomously finish some tasks without human intervention, like some focusing on planning and reasoning of specific tasks to reduce human workload, and some others work on integrating LLM agents into game scenario to serve as non-player characters. And some other works try to integrate generative AI into the XR. For example, one direction is to generate 3D models with the AI models. However, this approach is typically time-consuming and thus difficult to integrate into real-time systems. The other direction is to leverage large language model to create scripts and compile them during real-time systems. However, the script generation is typically error-prone, and thus a typical structure to deal with this issue is to have another LLM serving as the inspector and conduct an iterative loop to have a high-quality script to be compiled during runtime. However, this loop can be indeterminate and thus leading to significant delays as well as increasing costs when communicating with high-quality cloud models. The last direction is to create structured strings and use for function calling in XR systems, which is also the closest one to our paper. However, those works like a comprehensive framework with diffusion for XR environments. Beyond those works, the key observation in our paper is that extended reality tasks can usually be decomposed into a series of minimal reusable units. For example, when the user tries to create a solar system in XR, it can be decomposed into creating some objects, change colors of those objects, and create some orbiting animations. And if we have another task like create a moving car, it can also share with some units from previous task and have another executable units to be shared with the other tasks. Therefore, we can try to define some functions to let large language model to generate structured JSON data and then fed them into a predefined function and converts those data into real-time animations. However, this approach also faces with some challenges, like typical XR environments can involve tons of irrelevant information, and those can distract the LLMs. For example, if the user wants to place a calculator onto a table, there may be several tables, and it's difficult for them to accurately identify which is the correct one to create the objects. The other challenge is that this approach can be treated as a projection from the large space of script generation into a shortcutted XR tasks creation with JSON data. This projection constrains the search space for faster response and fewer scripting errors. However, it also limits the generality of this approach. Therefore, it requires a careful design to balance the benefits and the projection loss. To resolve those challenges, we then propose our system LLMER that connects external users with the large language model cloud servers. In our system, the user can simply talk with a virtual agent through natural languages, which is triggered either by a specific hand gestures or clicking the buttons in controller. And then the audio data is recorded and transcribed into text through the cloud whisper model. The transcribed text is then incorporated into a multi-stage process and communicate with the Cloud GPT-4 model to generate structured responses to be executed by dedicated modules. And we will discuss all those details later. And during this conversation, we also let the cloud model to create some artificial speech to mimic the natural human conversation. One of the key design in our paper is the multi-stage process and the context library. Specifically, we will process each user request into two stages. On the first stage, we name it the initial stage. Large language model will determine the category of the user's request and as well as the context. It will also split the complex request into multiple smaller requests. And the initial stage provides the category of the context. We then communicate with the context library to provide only necessary contextual information to be incorporated into the prompt of the refined stage. And then large language model will return the structured responses to be executed by the following modules. One important thing here is during both stages, we will define JSON schema to limit the responses. And in latest large language models like GPT-4o and o1, they support structured output to enforce the responses to follow the defined JSON schema. To handle various requests from the users, we define three dedicated modules to execute different tasks. The first one is the virtual object creator. We can create virtual objects from either Unity primitives or loading local resources or 3D models. We will let large language model to provide specific properties and leverage Unity's physics systems and conduct some post-processing to ensure the desired output. The second one is the animation library. We have defined a series of minimal action units like movement, rotation, or scaling. And those animations can be freely combined by the large language models. The LLMs will also provide specific properties to executing those animations. We try to leverage different coordinate space and Unity coroutine to ensure a seamless creation of those animations. And the last one is the reality fusion engine. This part will handle all of the interaction with real-world environment and human bodies. Also, it enables the creation of grabbable objects and drawing and recognition on virtual whiteboards. To evaluate our system, we conduct a preliminary user study with 8 graduate students. We let those students to wear a Meta Quest 3 and enable the pass-through mode to ensure they can see the real world. We conduct this user study into our laboratory, which is a typical office room. We let the users to have a 10 minutes training session and followed by 7 tasks in different difficulty levels. During this task execution, we will collect the task level usability metrics. And after that, we will let the user to fill out a questionnaire with dedicated questions for evaluating various aspects. And finally, we will conduct a semi-structured open-ended interview to collect the feedback from the users. So for the usability metrics, we measure from those 7 tasks, aiming for the various tasks like object creation or animation creation and the interaction with real-world environments. And we have collected the task completion time as well as the fulfillment levels for each task. We can see that most tasks are completed successfully or with minor issues within 3 minutes. Here, successful completion means the generated output perfectly aligns with the user's request, while the minor issue means a slightly error, maybe like the generated size is slightly counterintuitive or some other minor issues. And we counted that the consumed tokens is only around 3,300 for each request. It's about over 80% reduction compared with the script generation approach. As for the questionnaires, we evaluated 7 questions from like immersivity, interaction, or responsiveness, as well as other metrics. And we can get a pretty good score from all those questions, ranging from 5.25 to 6. So in conclusion, in this paper, we have designed the LLMR that accepts natural language inputs, specifically the videos from the users, and then leverage a large language model to automatically craft interactive extended words. And to facilitate the research area, we have implemented on the commercial XR devices and open source onto GitHub. You can simply scan this QR code to visit our GitHub repo. And finally, we have conducted a preliminary user study to assess the usability of our system and collect feedback for our future developments. And that's all for the presentation. Thanks for listening. If you have any questions, please feel free to let us know during the online presentation session. Thanks a lot.